Alright, what's up everyone? Welcome to another video of Modeling Methods Online. Today we're going to be talking about project number 6. I have the files right here. So what to expect for this project as far as file goes. Once the actual project section on web course is open, we're going to provide you guys with a PDF describing the project just like always. You're going to have a function file which is going to have the function that we're going to be using for this project, and we're going to have the Gauss Quadrature M file, which this is the main script, the one that we're going to be running. Right now it says Gauss 2 points, but we're in the project I'm going to go over, we're going to be using 5-point Gauss Quadrature. So the names of these files are not really, they're not relevant. You can name them whatever you want, but in a second I will show you why it's very important that if you change the files, you have to make sure that they match the way that the function is written inside of Octave. Alright, so let me open the PDF file. So this one right here is the PDF file. When I go over PDF files and when I go over these labs, the same that I used to, this is what I used to say every time I cover a lab in person. Do not get so caught up in the numbers, whether you're getting the correct numbers or whether you're getting different numbers. If you're getting the same numbers as I am getting in the projects, in the video, assuming that my code is right and I didn't make any mistakes, it's a good idea that you use it as an indication whether you're correct or not, or whether your code is working different than mine. Again, if I wrote everything correctly and there are no problems or no typos or anything like that, but the code, or not the code, but the values that we obtain in these videos do not necessarily reflect what you're gonna have for your answer sheet. So just keep that in mind. The same, I'm sure it's the same that you have seen in the last 5 projects. So this one is computer project number 6. We're gonna be working with Gauss Quadrature, which is the numerical integration. And the goal of this project, to simplify it, again, it's a good idea that you go over the whole PDF. It's only 2 pages. It doesn't take that much time to read it, but we're gonna be using a 5-point Gauss-Lagrange quadrature to evaluate the period. So this function right here, the function that we're given, this is a period function. This function calculates the period of the pendulum, and we're given some initial values. We're given the length of the cable, we're given the initial angle, so the initial displacement, and we're given the function itself. And the k parameter that we see here, that is inside of the square root, it's actually defined as sine 1/2 of the initial displacement. So all of this information is important. All of that, we're going to be writing it in our function file. This is also very important, the 5-point Gauss Quadrature, the weights, and this is actually the size. I'm going to refer to them as size because I cannot pronounce this for the life of me. But the psi values and the weight values that we're given, we're going to be using this for the numerical integration. So we will be implementing both of them in the main script. The questions that we're going to be asked is, we're going to verify, or MATLAB, in this case we're using Octave, but it's the same idea. We're going to verify that this works, which means that when we write our code, instead of perhaps using this is the goal of the project, we can call a different function. In that function, we can just type this function right here in that function file and change the evaluation parameters, the boundaries, the a and the b, the limits of integration. That's what I was trying to say. And we will type that result in here. Then we can report, you also have to report the computer value compared to the analytical, which is the exact value of integral. If you go over the class notes, if you go over the material, you should be able to understand and evaluate an exact solution of this integral. And the objective of this lab is to show you how to do the numerical approximation of the integral, so that later on you can see how they're different, but they're not that different. Like you will see that the numerical approximation is actually very, very similar to the analytical or exact solution. They're not far away from each other. And then we will report the computer period of the pendulum. That is the function that we're given. We will use a single interval for the quadrature. That means we're going to go from 0 to pi over 2. and then we're going to use two intervals and we're going to add them to double check that we actually indeed get the same answer from this one. So we will evaluate it in two different parts, and if you add the result of the calculator of the period for those two, you will get the same result as in part A. So you have been provided a working set of MATLAB files. I believe I will show you the files in a second, but in Canvas I do this project, blah blah blah. You're given a 2-point Gauss-Lagrange rule, and we're given a test function. So that is pretty much everything. This doesn't hold anymore, but that's what we're given for this project. All right, so I'm gonna go ahead and open Octave. This is Octave right here. I already have where my files are. I'm gonna go into project 6, and I'm gonna open the two files that I'm given. So I'm given this one and this one. All right, so this one, the Gauss 2-point, this is my main file. This is the file that I will be running my code from. And this file ftest, this is my function file. Let me maximize this. But as we read on the PDF, we're given a test function, and this test function has the form y equals x squared. So we will be modifying this to evaluate what we want for the project, and then the Gauss 2-point, we will be adding information to this file. So as I did in the previous video, let me make some room in here. As I did in the previous video, I'm gonna put the PDF side by side, so I go over the different parts of the project, and you can just follow along. And if you have any questions or concern, feel free to send us an email, and we will help you as much as we can. But I think the first thing that I'm gonna do is I'm actually gonna put an end statement here. This is kind of like driving me insane to see a function without an end statement. Something important to notice here is that I mentioned before that you can change the name of these files, and that always holds true. However, if I want to change the name of this file, this f.test, let's say I go over here, and I believe I can rename them from here. So let's say I want to change that file, and instead of call it ftest, I'm going to call it function.m, or let's see, I want to call it pendulum. Let's call it period underscore function. Way to make it complicated. If you do something like that, it's very important that if the name of the file changes, the function file also reflects that change. So this name and the name of the file have to match. So if I change that to say period function, I also have to change this to say, not that, period function. Okay. So let's see, let's just double check. If I were to run this, I believe I have to call the function here. So period function. And if I run this, I should be able to get, there is the evaluation. Okay. So what I did is I changed this. I will get back to this in a second, but this is the function that I'm calling in this point. So I have to make sure that it reflects the file. So this is the name of the file that I'm calling. I'm passing x as an input. That's what I have up here. But don't worry about it for now. This is what I wanted to show you, that whatever I name my file as, I also have to have that function file be the same. Otherwise, it's gonna give you an error. So if you're changing files because you want to call them something different, just make sure that change reflects in the function itself. All right. So I'm gonna start by I'm gonna go section by section, just define all the different things that I need. So I'm gonna create a comment in here that says define constants, and I will create the value of L 3.45. I'm gonna create the value of theta naught, so I will call it theta, let's call it theta sub 0. And then this is gonna be equal to pi divided by 4.5. And then I also have that k, it's equal to sine of, in this case I'm gonna do 0.5 divided by theta naught. Not that. There you go. There should be as far as the functions. I'm sorry, as far as the constant goes. Now I'm gonna define the period function. That's what I'm gonna use right here. So this is gonna be 4 multiplied times the square root of L divided by G. I have to remember to define what G is. And this will multiply 1 divided by, and then I have all of the stuff that is at the bottom, square root of 1 minus k square multiply times sine of x. In this case I'm gonna use x just because that's what I was using before. That is my independent variable. My independent variable is passed as x. I'm gonna keep it as x, even though it's supposed to be theta in this case, but I'm gonna leave it as x. So that should be, I believe everything should be fine. I have to define my g, and g is the gravity, so 9.81. That's the value that I'm gonna use for gravity. So those will be my constant values, and then this is my function from the pendulum, square root of L over G multiply times 1 over the square root of 1 minus k square multiply times sine of x square. Let's see, yeah. Okay. Alright, so that will be as far as my function files goes. So just a little recap, I define my constant values. The constant values are the ones that are going to go into my period calculation. This function again is the one that calculates the period of oscillation of the pendulum. And the reason we're doing this is because this integral is extremely complicated to evaluate. So I wrote everything in here except the integration symbol and the d theta. It's just this constant that is sitting outside, and then my function of interest. That's what I wrote in here. All right, so now I'm gonna go into this, into the main file. And in the main file there's an explanation. This is a 2-point blah 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 blah. So I'm just gonna show you pretty much what you need. We start by doing the clear, close all, and CNC. Like I mentioned in the previous project, this is very important. This is a very good practice. Again, you're clearing the workspace of any input from before. You're closing all your pictures, graphs, anything that you have open, and CLC will clear the command window. I'm sorry, clear will clear the, I believe I say workspace, so all your variables that you create so you can reuse them, and then CLC clears the command window. So the first part here, we're gonna define our weights, which are these guys, and we're also gonna define the psi values. And what this is doing, this w equals 0 to 1, it's creating a vector of dimension 2 rows by 1 column, and zeros just pre-allocates the memory for that vector. It creates that vector and it puts zeros in all of the components of that vector. This is a good practice for code optimization, especially when you have vectors that are changing dimensions, vector of matrices that are changing dimensions because of loops. As we have seen, we're gonna see it more, but in some of the iterative codes that we've been going over, we always think about, for example, a residual vector. A residual vector, if you only have 2 iterations, your residual, you only have 2 components of that vector. And then when you do a new iteration, then the dimensions change. Now you have 3 rows on 1 column. Then you keep doing more and more iterations. That vector keeps increasing in size. So it's very important that as that vector increases in size, we can pre-allocate the final or the dimensions that vector will have. It's just a matter of memory efficiency. If you don't want to write this, if you want to take it out, it's up to you. There's not going to be any problems with that as far as the code goes. It's just a matter of efficiency. So because this is a 2-point Gauss quadrature integration, this is my first weight, this is my second weight. I have 5 different weights, so I'm gonna go ahead and add them. There you go, and I'm gonna use the values from here. Now I'm very curious if I can just copy paste them. That will be extremely ideal, and I can. I am very happy. So I will take the values for the weight and those will be the component of my 5 by 1 vector. I definitely don't want to type any of this by hand because I always make a mistake every time I type in something. So in the same manner, we're going to define the psi values. I already mentioned what this is, so we're just going to write them again and write all 5 of them. So psi 3 is equal to that, psi 4 and psi 5. And in the same manner, I am going to grab each one of the values, and I have to make sure that I change this, that I change the dimensions for the weights and the zeros. I changed it to be a 5 by 1 because I have 5 components, and this one a 5 by 1 because I will write 5 components. So I will take that value and I will replace it for the first value that I have. I will take the second value and replace it. This one is just 0. You can just type 0, or you can be extra and type all those zeros like I'm doing. And this one will be a minus, and then the actual value. This one also be a minus and the actual value. All right. So that takes care of that. That takes care of the zeros of defining the weights and the psi. I went from having 2 to having 5. This is a 5-point Gauss quadrature. I'm initiating the value of the sum to 0 again, so I can reuse the variable. This is more of a C programming type of doing. You can always just use clear so you can use it again, but you know, it's just a good practice to do it like that. Then let's see, I have my integration from 1 to 5. The integration of this is from 0 to pi over 2. 0 pi divided by 2, and then here is the actual Gauss quadrature process. So for I equals to 1 to n, this means that it's going to run 5 times for each of these guys. There are 2 ways for you to write this n. If instead of having to write 5, so you don't have to change the dimension every time, you can do something else. You can do rows of psi, for example. You can do rows of psi, which is going to take psi and going to see the dimensions of psi, and it's going to say, oh, psi is 5. Those are how many rows this has. So that is going to make this value be equal to 5. Another thing that you can do is, instead of doing that, you can use the size function and then say psi in the 1 dimension. 1 dimensions, it means that it's going to scan the rows. If you were to say 2, for example, it's going to ask for it's going to tell you the number of columns it has. So if you do 1, this is the exact same as what I wrote before, rows of psi. So it's up to whatever you want to do. I'm going to keep it as 5 just to keep it simple. But if you want this guy to be self-updating and reflect everything else that you're changing, you can just type rows, or you can type psi, size of your variable, and then comma 1, so it knows that you want to go into 1 dimensional. So 0 to pi over 2, and this is the actual process that I talk about. 1 over 1 to n is gonna calculate this right here. This is called the Jacobian, b minus a divided by 2. It's gonna multiply by the current component of the psi. So as this guy changes, this is a for loop. As it goes through from 1 to 5, this x vector is going to increase in size, and every time it's going to calculate for a new value. And if the first value is going to take, the I is going to become a 1, so it's going to use this first psi, and it's going to add b plus a divided by 2, and then sum will become the previous value of sum, which, because we zeroed out, it's just going to have 0 for the first iteration. And then it's going to add the value of the weight multiplied times the period function. And the period function, this right here is very important. You have to make sure, number 1, that you are passing your x, which is the input. That is what we're calling as the input for the function, which is this whole definition. This whole thing gets passed as an input for the function. And period function, this function right here, you have to make sure that this name that you type in here matches the function file. it matches this phi. Otherwise, it's going to tell you it has no idea what it's looking for, or it's going to tell you, hey, this is not defined. So make sure that this name that you have up here, in my case is period function.m, that matches what you're calling down here. So then let's see, we're going to compute the Jacobian and complete the evaluation of the integral. So that will be the computation of the Jacobian. And that I believe that is everything. Sum will be multiplied by b minus a divided by 2. And we're going to be printing to a file. We're going to print the result to a file. So the file is the one that you're going to be submitting on web courses. And this is one of the things that I do want to change. The test function is actually the pendulum function. So you can either type that. In my case, I don't really want to type that. I'm not interested right now. I just want to see the output of the file. So I'm going to suppress that for now. Function is integrated from a. It's equal to. I want to talk what this means. So the percentage sign. Every time you're printing something, or every time you're try to output something, I'm sure if you took Intro to C, you're familiar with the data types. So the percentage, it just tells me that I'm assigning what kind of data type it is. In this case is F, which is a floating point. The 0.2, there is the point in here. The 2 next to the point, to the decimal value, means that I want to go 2 significant figures after the decimal. So if I were to type 2, it will be 2.00, for example. The 7 in front of it adds blank space. It adds like white space in front of my answer. So if I want to add a space or like a distance from the point where I say equal, I can specify in here, rather than have to type on my output and then just put a bunch of space. I can just say, hey, provide me 7 white space units towards the right. If I were to put them in the negative, it will subtract that space. Because it's a positive 7, it pushes towards the right. And then this is just a new line, and the percentage 7.2f, what I'm pasting here is the value of a. So that's the value of a. Same idea with the value of b. And then the 2 point, this one actually changes. This is a 5. This 5-point Gauss quadrature evaluation, it's gonna be the result. It's gonna be what I have as the sum variable. So if I go in here and I just run it, let's see what I get. So I wish I could maximize this. Function is integrated from a equals to 0, so b equals to 1.57. 1.57, that's pi over 2. And the 5-point Gauss quadrature is giving me 3.8429 seconds roughly. So this is the value of this integral. That's the value of this function using this weights and using this psi values. So if I want, for example, to answer the first question, verify that your MATLAB code works by using it to integrate this function right here. So if I want to do that, I will take this function, and I don't want to erase it, so I'm just gonna make it a comment. I will take that function y and say 6.25 times x to the 10 plus x cube. Alright, so that will be the function, and these constants are not being used for anything, but that will be that function. And then I will keep the same weight, I will keep the same size because they want me to verify using the same thing. And I will go into a and b. A is going to become -1 in this case, and b is going to become 4.5. So if I run it, then I can go into my command window and I can see function is integrated from a is equal to -1 to b equals 4.5, which are my limits of integration. And the 5-point Gauss quadrature is going to give me this value. So this is the integration of this, and you can verify this value using your calculator or using any other sort of integration platform that you want to use. But that is the value using these 5 weights and these 5 psi values. So let's see what else. report the computed period of the given parameter. So we use a single interval for the quadrature. That's what I did before. And what you can do for the second one, and I think you should be perfectly capable of doing the second part. You can do this process twice. This process that you see right here, and you can assign the value. You can assign one of the values that you obtain from one of the iterations. Like say you want to do this one first and then this one. So instead of having only an A and a B, you can copy this whole thing. You can do it twice and call your first limit A1 and B1 for the first set of integration and run this for loop. And then you can run it again for an A2 and B2 and just use different variables for your sum. Like all these different values that you're using, you can either use the clear like I showed you in the previous lab, or like we talked about before, you can clear things before you move on. If you want to reuse all of these values, let's say for example here, I want to, I don't know why that's following me, but let's see. Never mind. So if I want to say, hey, I want to reuse the value of A and B, you can always say clear A and clear B. This should be able to work. Maybe it doesn't. Undefined. Okay, so maybe it's not like MATLAB. I guess it is not like MATLAB in that aspect. Just create new variables and write those guys down, and at the end just add the two output. Like for example, let's say I want to call this one sum1, and then if I redo this and I call the second one sum2, you can just add both of them. You can print each of them independently. Just copy paste this guy again, just copy and paste it again and say, hey, the integration from this to this is equal to that. And you can also add both of them and show it that you did it correctly because it gives you the correct output. But that should be it for the project. If you have any questions or if you run into any issues with respect to that, just send me an email, send me a message to Web Courses, and I will help you. I will try to give you as many hints as I can, but it should be extremely doable. This is pretty much the code for the project. So that's it. Just if you have any questions, like I say, feel free to send me a message, and I hope you have fun and I hope you found this helpful. Thank you.